All right, today we're going to talk about calculations with titration curves and what to do in different situations. It can get complicated if you are confused and you don't know what you have and what you are working with. So today we're going to talk about a strong acid, strong base, and then we're going to talk about a strong with a weak. So first, in the upper left here, just to make sure that you're understanding the look of what a titration looks like, is that first off, the whole point of it is to find an unknown of a solution using a solution with a known amount. So you know a concentration of one, then you can find the unknown concentration of another solution. So, or the identity of it. So here's the analyte. That's the unknown. So this is the analyte. You're analyzing it. That's how I kind of like to think of it. That's in your Erlenmeyer flask. The titrate, or what you're titrating, is in your burette, and that's your known. So there's a little bit of vocab that's really important, okay? We have this graph on the right. Don't worry about what I wrote here. We'll add that. I'm doing this a little bit differently, and I'm restricted due to being stuck at home. So I'm going to actually reveal my notes as we go. So here we go. We're going to take 50 mils of a 0.2 molar nitric acid solution with a 0.1 molar NaOH solution. Now I know you're thinking, wait, you know both of these already. How? That doesn't make any sense. I understand that. But what we're trying to do is create a curve that we will do in lab later. So we're going to act like, well, let's take a look actually. Letter A, I wrote no NaOH in 50 mils of HNO3. Okay, so which one do you think is in the Erlenmeyer flask? Well, because there's no NaOH yet, it would make sense that the NaOH is in the burette. So I'm starting, this is my beginning point, with an Erlenmeyer flask that has 50 mils of my acid, okay? So I haven't added anything yet. So what we're gonna do, if you look up top here right now, is that we're gonna make a graph eventually of how many milliliters of NaOH I added. So what you can just do is I roughly estimated third, every third is a 50, so 50, 100, 150, and then I put pH right in the middle, a pH of 7, okay? So this first one, it's of just simply a strong acid. So if it's of just a strong acid, then there is no issues with pH, because if I'm saying that I have 0.2 molar of it, right, 0.2 molar of HNO3 is basically 0.2 molar of H plus, right? So that one's pretty straightforward because there's 100% dissociation. Then I'm going to plug this in, and I get a very low pH. So I have a pH of 0.699. And what we can do is we can actually plot that point then. So we're going to do that right now. So at 0 NaOH, I have less than 1. So I'm going to put a point right there. Okay? All right. So that, unfortunately, was the easiest one for us. It only gets trickier. So let's talk about what we're going to do here. So next, I'm going to add 10 mils of NaOH. It's very important for you to realize that you are starting over. You don't think about this first part anymore. It's like this is the only problem. Basically, the question each time is, what is the pH of this situation? So what is the pH of letter A? What is the pH of letter B? What is the pH of letter C? So if I have 10 mils of NaOH, what happens when an acid and a base react? They neutralize. H plus OH minus give water. So what we have to figure out is which one runs out first, okay? So I'm going to introduce you to something that's pretty cool. I think you're going to like it. So if I have H plus and I have 0.2 molar, okay, I don't know what I'm all showing here. Oh, here, sorry. This is the reaction that we're going to be doing. So we need moles of A and B, of my acid and my base, okay? So I want to know how much of my H plus and how much of my OH minus. So if you take molarity and you times it by milliliters, like what if you took molarity times liters? Don't you get moles? Well, here's a little trick. And in the beginning, you're going to kind of wonder, but I'm going to introduce a new unit to you today. Because everything's in milliliters, why keep converting milliliters to liters and then back to milliliters? So if you just multiply molarity times milliliters, you're going to get a new term called millimoles. So I have 10 millimoles of H plus. And if I take the 0.1 molar of NaOH, which is right here, and I multiply by my 10 milliliters of what I am saying I'm adding, then I hope it would make sense that I have 1 millimole of OH minus, right? Well, 10 millimoles of H plus and 1 millimole of OH minus, what do you get? They consume, it's not 11. You have 9 millimoles left of H plus. Okay, so now, once I have that left over, that's a pure H plus. So now, what I can do, and you got to make sure you're doing total volume, is that now I just put it over the total volume, and I'm going to get 0.15 molar of H plus, and I get now 0.82 for my pH. It should go up a little bit. Okay, so let's plot that as well. So now I have, this is really important for you to just understand where I am. I have 10 milliliters of NaOH at 0.82. So I'm going to go 10 milliliters. So that's going to be about here. 10, 20, 30, 40, 50. I did count that up right. It's not going to move much. Maybe right there. Maybe it's a little higher, maybe it's a little lower. It's not a huge deal right now. Okay? All right. Now, let's keep going. So now the 30, you're going to see a very similar situation. Instead of 10 milliliters, I'm going to add 30. So 30 millimeters of 0.1 molar is 10 millimoles. Now, what is really cool about this, guys, is that my acid never changes. I started with this amount. So I already have 10. I don't need to keep showing that work. So now what do I have left? I have 7 millimoles. And what am I going to do? I'm going to take my 7 over my total. So what is my total? My total now is 50 plus 30. So now I have 0.0875 molar H plus. So now I'm going to take negative log of that. And now I'm going to get 1.06. Okay, pH isn't changing much because it's still pure acid sitting there. But let's plot that too. So 30 milliliters, 1.06. 30 milliliters, 1.06. So I'm just over 1 now. So it is going up. Okay. All right. We only have 2 left already. So we could do a lot more steps. We could do a lot more plots. But now we're kind of jumping into it because I want to just show you the differences here. So here we go. I have 100 milliliters of 0.1 molar, which equals 10 millimoles of OH minus. By the way, I did not state this. If I take millimoles and then I redivide it over milliliters, the M cancels and I have moles over liters. That's the whole point of millimoles. Okay? You get molarity still at the end. And then what do we have? We had 10 millimoles of H plus. Well, what does that mean? Well, what that means is that I have equal amounts. And what that means is a very big word. It's called the equivalence point. Some people call it the end point. So, you've heard of this before? Excuse me. If you have equal amounts, that's what this equals. M1V1, or MAVA, when you multiply moles times volume, or molarity times volume, what you get left is moles. So I'm basically saying moles of A equals moles of B. Moles of A equals moles of B. I have equal amounts. So what I can do is I can plug this in. Also, just so you guys know, we also want a color change. So unfortunately for this one, we can't really compute this. And the reason why is that, you guys, this is a strong with a strong. So that's going to be 7. When there's a strong and a strong, it perfectly equals out, and we're going to have a pH of 7. Okay, so we're going to go back to that again. So I have 100 milliliters of NaOH, and the pH is 7. So let's go back up to our plot. So I have 100 now. I'm going all the way to 100, and I'm going all the way to 7. Boom. All right, last one. So now you kind of have an idea what's about to happen. We're going to have more than we should for this. So now we have 15 millimoles, right? Well, and we only have 10. So now I have 5 millimoles of OH in excess, right? So now, what does that mean? Well, first, I still need to put it over the total volume. So I'm going to have 0.025 moles of OH. So what would you think you do to find the pH? Well, it's what we've been working on before. See if I have anything else hidden there. So I'm going to take POH equals negative log, and I'm going to get 1.06, and ultimately I will get 12.04. So let's go graph that. So I have 12.04, 12.4 with 150. 12.4, so 8, 9, 10, 11, 12. So now, you're probably wondering, what does this look like? Well, you've been given a reference guide of what titration curves or pH curves look like. So what you got to realize is that there's a huge leap right here, and then it kind of falls out. So technically, what I would have loved is to have done some sort of work right there, and I would love to have done some sort of work right there. What I mean, something like 80, and I would like to have done something like 110. Why? Because then I can know where this comes out of and where this goes in. But I don't have that ability right now. We didn't do that. So let's just talk about what we have. You have to estimate then. So what you're going to do is you're going to follow the line, and we're going to do the best we can. And I'm using a computer here, so this isn't the easiest. So it probably looks like something like this, and then it jumps up, and then it flattens out. Whoops, I missed it a little bit. Sorry about that. I can try one more time. And I'm using a mouse pad here, so I'm not the easiest. Wow, that's worse. So that's what that looks like. Again, you have a lot of times a strong kind of looks like this, and then it goes up, and then it flattens out. Like that's very exaggerated. But that is a strong pH curve. And the next one we'll do in the next video will be a strong, weak pH curve.